So let's get started without any further ado.
Okay, so sorry for the delay. My name is Patrick Vonwirth from the RPTU Kaiserslautern Landau, brand new rename since January. And first of all, here's some advertisement, because next year in September we are hosting the Lava Conference in cooperation with FZD Karlsruhe, so it would be nice next year in September for the climbing and walking conference to see some of you guys at my university.
What are the exact dates?
Sorry?
What are the exact dates?
Probably second week of September. This has been decided last week, so this is now in the process to get started. Okay, I'm working on a bipedal robot. Wow! It's a lower body, it's a planar, quite simple thing, and we're focusing on the propulsion system actually, so especially the motors, and we try to mimic the natural muscles, because we just heard in the talk before that a natural muscle is controlled in a way worse manner than we can do with the electrical system, but they work quite well. So the question is, how is this done? And here I borrowed a nice graphic from the biomechanics book by Winter. We have a characteristic of a muscle. Let's say a characteristic of high range properties, so neglecting all these short range stiffnesses and all this stuff. And we see more or less two properties. One is a stiffness property and one is a damping property. And if we check for the stiffness property, we see that we have two sides, which means on one side we have a negative stiffness and on one side a positive stiffness. And if we think about a negative stiffness from control side, we quite fastly stop thinking about that. But there is the other thing about damping, and damping has this nice effect that is independent of the directions. And so this damping is always positive. So what our idea is to probably go with this damping as one big characteristic of a natural muscle to improve the controllability of our body. And now we have, let's say, the following. We take two antagonistic muscles and we have the forces which are acting in the opposite direction. So the forces are subtracted. But if we check for the damping, as I said, the damping is independent of the direction of motion. These damping values are actually added. And now we have, let's say, some system with two antagonistic muscles, two input data, and two kind of independent output data. And which means we have two inputs, which are responsible for a force in both directions. And we have both of them being responsible for a damping. And this damping can be used in case of co-contraction to stiffen up our system. And this may or may not be one reason why we do this actually, why we have all these muscles. And what is the reason behind? Because technically one actuator per joint is absolutely enough, can do everything. But with these low control speeds, nature has to have some clever mechanism to overcome these big delays we have. And if we go with this, you might have already read the term of a so-called preflex. And if we go with this, we kind of are able to program our body to physically react in a proper manner to disturbances which might happen in the future. And because this is a built-in property into the muscle, so zero delay. We just have to set up our body before. this is good motivation. We tested it on a single motor, which was working. We tried to test it on a full bipedal robot, still in progress. Because the problem is, as we already have noted here, we have a system which is adaptive impedance system. We also have a spring in our motors because we are trying to mimic natural muscle. Natural muscle has a tendon. And yeah, getting all this a little bit into a controlled manner with no passive springy reaction force is a little bit of a problem, as long as we don't want to overdamp our system. I mean, obviously we can just stiffen it up, but then we have the same as before. Okay, so time is over. I think we can go over to the questions.
Did I understand correctly that you have one motor for each muscle?
Yeah. And maybe I can go back here. So we also have an over-actuated system, yeah, as we see it in nature, where we have monoarticulars as well as biarticular muscles, which has the benefit that all these different stiffnesses kind of stabilizing itself, yeah, because you get some very weird motion out of it. That has also the problem that you somehow have to control it. Especially in the force domain. In the domain of the damping, you need these because every single actuator can only act one direction, obviously. And if you need to really preset your system for a specific situation, you need, in theory, one actuator for every single direction. Otherwise, you can only get close to the stuff, which means the more versatile actuators you have in your system, the better you can approach to the desired stiffness you want to have, or impedance. Yeah.
Yeah, my question would be, in the control of your actuators, are you considering muscle properties?
We're considering muscle properties in a way that we try to damp, and we are only damping the contractile element, not the spring. And we have the spring and the force. But we do not have special force characteristic curves or something like this. Because this will be highly nonlinear and difficult. Maybe
Maybe so. Do you have antagonistic muscles? Are your motors? Are they attached in some way?
No. We have. I mean, we have an electrical motor.
Okay.
So this is both directional. Yeah. So this is represented these muscles. Yeah. Then maybe.
Are you doing some sort of static optimization to obtain the force of the spring muscle?
So we have to distribute the forces. We have some quadratic optimization running, but let's say this is not the main focus. I mean, obviously you can distribute the work to different muscles, probably save energy, because if you only have special muscles, they may work against each other. So there is such an algorithm running, distributing this, but this is not the main focus to get, in this case, energy efficient.
I think we're on time. I think we're about out. So, but it looks like there's a lot of time for questions. Thank you for your improvisation.